Hi, my name is Kunal Marwaha. Today I'm giving a talk on approximating the max kXOR problem with both quantum and classical algorithms. This is joint work with Stuart Hadfield at NASA Quail, and also I was at NASA Quail for a summer internship. So what is the max kXOR problem? So this is a constraint satisfaction problem where you have n Boolean variables, m clauses, and every clause is of a certain form. You take k variables and you check the combined parity and see if it's odd or even. So in general, you may not be able to satisfy every clause, but you might want to find an assignment to the Boolean variables that satisfies as many clauses as possible. So I'll be looking at algorithms that attempt to approximately solve this problem, both from quantum computing and from classical computing. One way to look at these clauses for kXOR is to see a hypergraph where you take every clause and you look as if it's a hyperedge. So on the left side, you have 3XOR, where you have a clause representing with variables 1, 2, and 3, 3, 4, and 5, and 5, 6, and 7. In this work, I'm going to be mostly looking at regular graphs. So notice in the right side, every variable is involved in exactly 2 clauses. So it's still a 3XOR problem, but the variables are involved in the same number of clauses. Also, because this is analytic work, I'll be making an assumption that's kind of like the triangle freeness or the high girth assumption. For kXOR, this is ended up called no overlapping constraints, where it means if you have 2 variables, they can, if they share a clause, they don't share any other clauses, and none of their neighbors are shared. It turns out if you make a different assumption that all of the clauses have random parity, even or odd, with probability 1/2, the analysis for both of these algorithms is the same. So there might be some deep connection here between the triangle freeness, no overlapping constraints, and also random signs on the clauses. And I'll be looking at local algorithms, and local has a lot of meanings. Here, I don't mean local search. I mean something else. So I mean an algorithm style where you randomly assign each Boolean variable, and then you reassign it only knowing its neighbor values. So only knowing the variables that are involved in clauses with x sub I, then you can set x sub I. So it's local in the sense of the graph picture of this constraint satisfaction problem. And you might hear something like depth P algorithms or P local algorithms. And usually I mean that you're repeating the second step P times. So this definition can work for both quantum and classical algorithms. So I'll start by looking at depth 1 algorithms. These are 1 local algorithms. I'll be comparing a popular quantum algorithm with a kind of similar classical algorithm that should be competitive with. So the QAOA, or the quantum approximate optimization algorithm, is a really popular near-term quantum algorithm. So it runs an iterative cycle where it has a depth P, and as you increase the depth, you're going to get better and better performance. But because you can set the depth quite low, you might be able to run them on small quantum computers that we have today. So this is a combinatorial search optimization algorithm. So it can solve problems like max cut or 3-sat, and we're going to use it for the kXOR problem. The analysis of QAOA theoretically is actually really complicated. And so, for example, before this work, nobody had done it max kXOR. So what we did is we found the optimal performance as a function of the hyperparameters of the algorithm and the clause density D. And we compared it with the results from the local threshold algorithm. And we chose this classical competitor because it's very, very similarly performing on the maximum cut problem. So both the depth 1 and depth 2, this local threshold algorithm is just outperforming the QAOA. And so we thought, is that true in this general class of problems, kXOR? So this local threshold algorithm, how does it work? So first you randomly assign each vertex or each variable spin, and then simultaneously every vertex looks at the clauses that it's in. And if it doesn't satisfy enough clauses, it flips. And you choose this threshold to maximize the number of satisfied clauses. Note that all of the decisions are happening at the same time. So you don't have information about somewhere else in the graph, just to your neighbors. This is the local threshold algorithm. If you want to increase the depth, you could run step 2 more than once, but in this talk, I'm just looking at one local algorithms. So this is the picture from the analytic work. After computing an expression, after calculating an expression for the optimal performance, you can see what it is on graphs with large d, large degree. And so on the x-axis, you have k, and on the y-axis, you have a measure of performance. And this measure of performance is the fraction of clauses that you can satisfy. And so on average, you can satisfy about 1/2 plus some constant over square root d as d grows larger. And for constant k, that's optimal. But notice that numerically, the QAOA actually outperforms the threshold algorithm when k is above 4. So what this says is that even though they were really competitive for k equals 2, like max cut, at higher k, the QAOA is much better than this threshold algorithm. That's surprising. But in the rest of the talk, I'll tell you why I don't think this is a huge accomplishment for the QAOA. So part 2, tight upper bounds. So if I give you a random CSP and I tell you it's a sparse random instance and it's large, how well can you do? How many clauses can you satisfy? And for many CSPs, there's a connection between the maximum number of clauses you can satisfy and some concepts in statistical physics. So the most famous connection is with the maximum cut problem. For a large, random, sparse graph, the maximum cut is 1/2 plus this p star over square root d, where this p star has been coming from the Sherrington-Kirkpatrick model, a spin glass model, where that p star is a ground state energy density of some physics problem. And it turns out this connection holds for kXOR and KSAT, and it might even hold for any CSP. And so there's some really deep research areas here that I think would be nice to explore. Can you turn a CSP and give you the optimal value that you can number of clauses that you can satisfy? So I think there's a lot of interesting stuff here. So how do you calculate this p star or this statistical physics concept? So you take a fully connected spin model and you're going to calculate some free energy or some ground state energy density. And this was relevant to some physicists in the 70s and 80s, and someone came up with a trick to solve it. It's a variational trick where you're minimizing over constant functions, piecewise constant functions. And it turns out this trick is actually correct. It does actually calculate the Parisi value. It's named Parisi values after this person who invented the trick. And there's a new way to calculate this formula that came out recently that doesn't depend on beta. You don't have to take infinite limits over infinite limits, but no one had done the numerics before. And so what we did is we calculated the numerics of these Parisi constants for all k, or at least k to 35 for the kXOR problem. And so this is what we get. So for k equals 2 and k equals 3 had been calculated before, and k equals 2 is proportional to this p star that I mentioned earlier. But you notice the Parisi constants saturate very quickly. So what this means is that this is the actual values from the statistical physics concepts that we can translate into the optimal value, or the optimal satisfying fraction of a kXOR problem. So the code that does this is open source. I'm happy to talk about it further. And yeah, you can ask me any questions about it afterwards. But this is what happens in the kXOR problem. It turns out that even though the QAOA outperforms the threshold algorithm, the optimal value actually scales with square root k. And so it grows a lot faster than the QAOA or threshold algorithm's performance. So this is the first reason why I'm not sure the QAOA beating the threshold algorithm is a huge deal, because there's so much room between the QAOA and the optimal you can do for a high K max kXOR problem. However, I should say that we're just looking at the QAOA at depth 1, and at higher depth, I'm sure it will do better. But it may be that other classical algorithms will also do better, maybe even the threshold algorithm at higher depth. So there's a lot of uncertainty here about what is the best you can do algorithmically for max kXOR and if a quantum computer will actually make that better. Okay, part 3, barriers for low depth quantum algorithms. So one way people try to talk about the QAOA at higher P, at higher depth, is they talk about obstructions. And what an obstruction is you identify a problem where the QAOA can't do very well, even as the depth grows. And so it's not saying on average the QAOA will be bad across all graphs. It's just saying there are some instances where the worst case success is actually very low. And so there is a known obstruction for QAOA on max cut, which is you can't get within a constant fraction of optimal until the depth is logarithmic with the system size. And so what we do is we extend this kind of neat proof into 3 XOR. And based on our extension, we guess that it's probably true for all K. And so what this means is that QAOA is not generally, amazing on all graphs. There are going to be some problems, some instances of problems where the QAOA is not successful. So it still may be that the QAOA is effective on some families of graphs, and there may be even quantum advantage. But still, there are problems where it does not do very well. So I should note our graphs that we create are not regular graphs, and I'll walk through the proof briefly, and you can talk to me more about it at the end. So there's a statistical physics concept called the no low energy trivial states that has to do with, has deep ties to complexity theory and quantum complexity theory. And what it says is, is there any Hamiltonian that you can't get to the ground state with a simple quantum circuit? And by simple quantum circuit, I mean this low depth quantum circuit that you can't get to the ground state if you start from some random product state. You can't find any of the low energy states. And that's why it's called no low energy trivial states. The trivial states are the ones you can reach with these simple quantum circuits. And there's a quantum PCP theorem that's related to the classical PCP theorem that kind of depends on this conjecture being true, that there is some family of Hamiltonians that has this property. So a lot of people study it and kind of are interested in the general application of this conjecture. So it turns out that the NLTS is true if you assume a symmetry. And if you assume this kind of bit-flit symmetry, which the QAOA unitaries have for max cut, then the NLTS property holds. And so then there are some instances of max cut where the QAOA is obstructed. This is how that recent obstruction was proven. So what we do is we turn this bit flip symmetry into kind of a partial bit flip symmetry, where we build off the family from the previous proof, and we turn it into a 3 XOR problem. We add sources and sinks, and we're able to show the same style of proof, that we show that the NLTS holds under a certain symmetry, and that the QAOA has that symmetry, and so it's obstructed until low depth, until logarithmic depth. And so because of this, we kind of assume, or we guess that it's probably true for all K. So this is the second reason why I'm not super excited about QAOA beating the threshold algorithm, is because there are some problems even across kXOR, at least for 3XOR and probably higher, where the QAOA will not perform optimally until its logarithmic depth. At higher depth, QAOA still may be useful, and it still may be small enough, log n may still be small enough where you're able to use the QAOA on a near-term quantum computer. But I still think there are a lot of unknowns about whether quantum computing is actually useful for this problem and broadly for many problems in optimization. So thanks for listening to my talk. I'm at the University of Chicago now, and you feel free to email me anytime, and have a nice day.